is Lab 4 for Physics 2212. Let's get into it. So for the introduction, the idea of the lab is basically just to measure the distance-dependent magnetic field of a bar magnet, and take that and using Biot-Savart law, using that law to compare the observed and predicted distances of the on-axis and off-axis magnetic fields. So the preview after experimentation with the lab, n equaled 3.2661, the magnetic dipole moment mu equaled 1.66 am squared. So the fundamental principles, concepts, the first one, Biot-Savart's law. This one relates to the magnetic field at a given point and how it relates to a small current element. Then the magnetic field of a dipole is just a magnetic dipole. It's a closed circulation of an electronic current system. And distance dependence formula described as the way the magnitude of the magnetic field to a bar magnet falls with a greater distance. And each of those three can be seen on the right. Those are the equations related to each. So then for the procedure, step 1, we just place the phone to make the magnetometer orthogonal to Earth's magnetic field, just get it in line. And then step 2, find where the magnetometer chip is located in the phone. In this case, in the example, it's marked by the red X. And then step 3, measure the distance between the magnet and the magnetometer for the on-axis and off-axis. And so for the on-axis, we basically measured different distances and different levels of electromagnetic field, and then we marked those distances and we created this table with the equation y equals negative 3.2661 x minus 14,918. So the calculations using that linear model, we were able to figure out what the magnetic dipole moment equals. Mu right there equals 1.66 am squared. And so for the off-axis, we did a similar thing. Kind of had a representation of what the off-axis and on-axis looks like on the right. For the off-axis, we also just measured different magnetic field values and where they equaled for a given distance. So then we had to do a computational model for it, just kind of demonstrating what was happening with the magnetic field. These were just the initial conditions with the magnet and the magnetometer. So and here's the computational model and just kind of the results. The on-axis is represented by the orange arrows, the off-axis by the cyan arrows, and then the purple arrows at the 45-degree angle. So potential errors, we had to make assumptions. The first was that the magnet behaves as a simple dipole, and the second is that a magnetic field falls as distance grows. And then potential errors, other devices in the vicinity may have skewed the data, and then the exact magnetometer location was estimated, it wasn't pinpoint accurate. So then observations, these were 4 observations we were given, and we had to determine which ones are true, which ones are false. 1 and 4 are true. When the magnetometer is far away, it measures a near zero magnetic field. That goes back to the fundamental concept we discussed earlier. And then the last one, as the magnetometer moves closer to the magnet, the measured X component of the magnetic field increases again. It's going back to the fundamental concepts of the magnetometer gets close to the magnet, then the values will increase. So what if we had oriented the experiment to compensate for magnetic north and instead laid out the meter stick at some intermediate angle with respect to Earth's magnetic field? How the results have changed? Would have been skewed since the magnetic field of the planet would have interfered with the magnetic field of the magnet. They're different values, so the data would have been different. And then what if we were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? The biggest thing is just that the magnitude would double, since the strength of the magnets would double, but the direction of the magnetic field would still remain the same. On-axis and off-axis, they would still have the same direction for the arrows. So that is it. Thank you for watching.